Dear student, Assalamu alaikum. I hope you will be fine. So, we are here in the Inorganic Chemistry 2 class. The course code for this is CH316. The credit hour is 3. This is basically course related to the study of transition metal, the coordination compound, or which we also call complexes. So in this courses, the major portion of this is the basically the study of transition metals, its importance, feature, characteristics, properties, and its importance compound that is called coordination compound. Some of the basics theory of the coordination compound, that is Werner theory, that is crystal field theory, valence bond theory, and some of the crystal structure are also, and the redox reaction and other topics are also a part of this course. So we have some of the reference book here also, which is some of the classical references, which are the Basic Inorganic Chemistry by Cotton and Wilkinson, Inorganic Chemistry by Shriver and Atkins, James Woohey, Inorganic and Ellen Carter, the Inorganic Chemistry, Principle, Structure and Reactivity. Also there you may find some of the online resources which you find better, or some of the new books. Maybe I have to send some of the reference to you on Google Drive. So this is little bit about the introduction of course, which have some of the topic which we have to study in this overall semester. The semester is now officially launched online, and we have also now arranged online classes for you. I hope you maybe received the timetable also. So accordingly, we have to join that later. First of all, in this manner, for example, let you may be familiar with the periodic table. In the periodic table, you may see here, for example, a group of transition metals. As you know from the periodic table, that transition metals are basically placed between the S block element and P block element. These are the S block element and these are the P block elements. So transition elements are also divided into two categories. One is outer transition element, the other are inner transition elements. This portion, for example, which you have a little bit pinkish portion, are called outer transition elements or normal transition elements, and this portion which have you see here are called inner transition elements. They are called inner because they are taken from here, from the number, as I explaining you. For example, you are seeing here a lanthanum. So lanthanum has a atomic number 57, and after lanthanum it is cerium, that is 58, and it end up lutetium Lu with 71. But here you see that hafnium is 72. So this means these elements are start from 57 up to 71. So it starts from lanthanum, that is why they are called lanthanized series. Similarly, down it is actinium. For example, actinium has atomic number 89, which you have seen here, and it's end with lawrencium, which have atomic number 103, and it starts from hafnium, that is atomic number 104. So this means that this series start from 89 up to 103, and these are taken from here, so that is why they are called embedded, not embedded, and they are taken out there. That is why they are called inner transition element, that is taken from inner area of. So you have to see here a number. So these are also transition elements, and they have different property a little bit from their normal or outer transition element. So this is little bit the introduction about you, little bit about the placement of the transition element in the periodic table. Now let's we have to start here a revise little bit you about the general electronic configuration. As you know, for general electronic configuration we use the Abba principle. According to Abba principle, we place various orbital according to energy level, and these energy level, for example, the orbital are fill up by the energy level. For example, as starting from 1s till 7s, starting from 2p till 7p, 3d to 7d, and 4s to 5s. So by this, if you see the path, for example, if you have element to fill up atomic number, you have start from 1s, then 2s, and then 2p, and then 3s, and then you have to go to 3p and 4s, and then you have to go back from 3d. These numbers are also set by some of the physicists, for example quantum mechanics, and quantum mechanics give you that system. Similarly, by that calculation we know that every orbital has their own capacity. For example, s orbital can accommodate just 2 electron, p orbital can accommodate just 6 electron, d orbital can accommodate 10 electron, f orbital can accommodate 14 electron, and they have their orientation also. S orbital has just single orientation, means that the 2 electron is placed in two in one orientation, and the shape of it is also spherical. For example, and the p orbital has three orientation: px, py, pz. D orbital have many orientation up to 5. F orbital has 7 orientation accordingly, and their shape are complicated too. For example, if we have made a journal representation by according to this path, so you may see here 1 is 2 this, 2 is 2 this, 2p6 this, and then from 2p it is 3s2. So here 3s2, and then again goes back to 3p6, and then again goes back to 4s2, and then 3d10. This is the maximum filled electron. For example, this is an imaginary example. For example, how much electron you may fill. So you see s is filled up to 2, p is filled up to 6, and d is filled up to 10. So we have to talk about a little bit orientation in the coming slides too. So here we have to see some of other concept. For example, that 1s orbital is lower in energy and 2s orbital is higher in energy, as you see by this line. So there is a gap. For example, as we see in the Abba principle, 1s orbital has to be filled first, and then 2s orbital, and then 2p orbital, and then so on. Here you may see that some of the orbitals are in the same line. So this is we call the degenerate orbital. So the degenerate orbital has the same energy. This means this is 2px, 2py, 2pz. So means that they have the same energy. We can fill the electron in any one of them or depend upon the availability of electron. For example, if we have electron more, we have to fill it more. For example, we have electron less, we have to fill it according to Pauli exclusive and Holmes rule. We have to discuss Pauli exclusive principle and Holmes rule in the lateral slides. So let me see one thing more. For example, here you may see a number 1s. So this is s orbital, a lower orbital, and 2s, a little bit a second orbital. But similarly, we have to learn here that 1s means 1 means principal quantum number. This is first shell also. First shell contain first orbital and just s orbital, but it is principal quantum number 1 first shell. This line represents second shell, and this line also represents second shell. So this means a second shell contain 2s and 2p orbital, 2s and 2p orbital. So this means the total electron here are 8. For example, 2 electron in the 2s orbital and 6 electron in the to p orbital. For example, each orbital can accommodate 2, 2, 2. So here you may observe total 8 electron. Similarly, the 2p orbital of the second shell is a little bit higher than energy from its neighbor 2s orbital. These orbitals are placed in the single shell, but this is the energy gap between them. So this is the same quantum number orbital. This is degenerate orbital within each other. For example, 2px, 2py, 2pz, but not equal in energy to its 2s orbital. If we see a little bit upward, here we have to see 3s orbital, 3p orbital, and they have also the 3 principal quantum number. The 3p orbital is little bit higher in energy than 3s, and then comes 4s orbital. As we go upper, you see the energy gap is little bit lower. This energy gap is we have to discuss in the electronic configuration of the transition element in advanced element. As due to this little gap of configuration, some of the orbital can overlap with each other, and they may make a disturbance in the electronic configuration. As for example, one thing let me clear that 1s orbital is smaller than 2s orbital. 2s orbital has a bigger structure, 3s orbital has more bigger structure, 4s orbital has more bigger structure, and similarly 5s orbital has more. So the bigger, as the structure can bigger, it correlates with the neighboring orbital. For example, this 4s is correlating with the 3d, or maybe correlating with the 3p due to its size. Similarly, this make a little bit ambiguity in the electronic configuration. So that is a little point. Let move further. For example, as we move further to the electronic configuration, so there is excitation also. For example, when one electron is placed in the one shell, if it gain energy, it's move toward upper orbital also, and this create an excitation of energy. So that is we called an excited state for an orbital. Now telling about something about the second portion of the electronic configuration, that is called Pauli exclusive principle. In Pauli exclusive principle state that no two electrons have all the same quantum number values. For example, there are many quantum number value: principal quantum number value, azimuthal quantum number value, spin quantum number value, or magnetic quantum number value. Here state that, for example, these two electrons are placed in the same orbital. So this means that they have principal quantum number value of a number they share most of the principal quantum number value, but here they have a different principal quantum, they have a different spin quantum number value. For example, if it is rotating clockwise, the other electron may be rotating anti-clockwise, so this is a difference. For example, they have principal quantum azimuthal, all the quantum number value same, but not the spin quantum number value same. So Pauli exclusive principle state that if you place two electrons in the single orbital, you have to show one electron down arrow. Down arrow means that its spin is opposite from its neighboring orbital in the same neighboring electron in the same orbital. So this you have to make a point clear. So the second and the last portion is Hund's rule. So Hund's rule is also state that if you have more electron in the orbital, that electron will go singly, not in the form of a pair. If you have the space, so you have to place it singly. So this is also called as empty bus rule also. For example, if you see here in example, this is orientation of p orbital. For example, this is 1p, this is second p, or third p. So literally p x, p y, p z. So if you have 4 electron, here is a placing, the 2 pair are here and 2 pair are here. So this placement is wrong. What is the correct placement? The correct placement is, for example, one pair is if you here there is the second pair, you have to put the fourth electron in the next empty orientations, for example pz. So now here if you see, here a single electron is placed here, a single electron is placed here, and a pair here. So this is a right way to place. Similarly, you have to be this place in d orbital also, or a higher level orbital also. That if you have a place not to put electron in the form of a pair, you have to put it singly. What will we get this from with benefit? For example, electron is free here to move, here is also free to move, but here you have no possibility, so it's okay to put a pair here. But here if you have one pair, it's okay, but this pair does not mean that you have to put this pairing cancel the spinning of the electron each other. So electron want to spin, so it have to be placed here. So this placing is means that we are placing the electron in the single orbital. So this by this Hund's rule, if we go filling electron, so we have to put it here. No, there is some other example also. For example, in case of oxygen, if you have 8 electrons, so for example 1s2, 2s2, 2p, 4, and this is for example generalized for example notation. So for example 2 to 4, 4 plus 8. So in this example, in this setting, you don't know that 4 electron how can arrange, whether they are arranged pair in the both of the orientation, or whether one pair or one electron is single. So here to represent 1s, so it is 2, so it is pair, there is no way to single it, so you have to pair. 2s, the number comes the second s orbital, it's also okay, you have to pair also. So as you know student, here are some of the ways which you will learn here about the electronic configuration, and see example of it, how the Hund's rule works. There are also one or more example too. As you see here are some of the configuration which is formed in the compact form or in the form of symbolized form. For example, here you may see the electronic configuration of sulfur. Sulfur has atomic number of 16, and as you see that this is divided into two colors. For example, One is the core electronic configuration. One is the core electronic configuration, and this core electronic configuration is the configuration of its neighboring noble gases. For example, this has 1s2, 2s2, 2p6, which makes 10 electron. So the 10 electronic configuration is basically configuration of neon, and further we have the rest. For example, we have 3s2 and 3p4 electronic configuration. The 4 electronic configuration we have to set according to the Hund's rule, as we learned in the previous slide. For example, 3p has 3 orientation, 3px, 3py and 3pz. 2 electron, a pair electron goes to px, and a single electron goes to py and pz respectively. So that is, it is makes the electronic configuration. By this you are knowing that electronic configuration can be done with the help of 3 basic small principle. One is aqua principle, the other is Pauli exclusive principle, and in the last one, that is a Hund's rule. So now we have to see the placement of periodic table a little bit. As you see that we have groups. For example, this is alkali metal group, a first group, and in alkali metal first group we have electronic configuration 1s1. For example, all the elements which are filling electron, the last one electron is filled with s1. That is why the both group, the yellow group, are called s block element, as their electronic configuration ends on s. But the first group called means that they have one electron in their s block, and when you goes toward the second period, for example, if you have talking about this, so in this we have 1s2 electronic configuration, which we may discuss maybe later. So this is a simple electronic configuration. Similarly, all the other color are filled accordingly. One, for example, this configuration, this example tell you that if, for example, the configurations stop on certain thing, we get some of the information. For example, if we have 1s1 electronic configuration, this tell us that the elements belongs to principal quantum number 1, for example this, and s depends upon s block, the block of element, and this first, for example, first column of the s block, as I told you earlier that the first block, alkali metal, all have ending electronic configuration on 1. So that is the first column or first group of the s block element. And if you have example, for example, if we have an example, there is sodium and there is helium, magnesium. So magnesium has ending electron s2. So this we have to get the information. So we have some of the pattern, for example, the journal pattern. So we have, for example, core electron, and core electron means that we have put a symbol of the noble gas, which is, as you see in the other. So if we have a generalized form, so we have to see that all electron ends up with the s orbitals, so they are grouped as s block element. And if we have normal transition element, the normal transition element have ending electron in d is equal to n-1, where n is principal quantum number. Here we have a p orbital, that all the element electronic configuration ends with p orbital, and here we have f block element. So f block element we have electronic configuration n-2, mean the principal quantum number value have less 2 electron in its f block f orbital value. Similarly, the d has 1 electron less than the principal quantum number of the original period. So this is a little bit a generalized portion. For example, we have an example of germanium here. So germanium is an example of P block. As you see, germanium is present here. So let's see, we have to do its electronic configuration. For example, we have here germanium. So germanium is, you see, belongs to 4th period. So germanium C belongs to 4th period. Let's see its last orbital configuration. Here you see the number 4. The number 4 implies you that it's belongs to 4th period. As you see here, it belongs to 4th period. Now you see here argon has a core electronic configuration. As you see, student, here argon is basically the ending neighbor of the last noble group, as coming toward the germanium. For example, argon has atomic number 18. So these 18s have to symbolize the argon. For example, if we are counting the electron or we are counting the position, we have to consider the number of argon, that is 18 electrons. So for example, we have to add, for example, 18 plus 2 20, 20 plus 10 30, and 30 plus 2 32. So it makes all 32 atomic number. Let's see again the last ending orbital and the number and what we have to interpret from it. Look, here is 4. So 4 means germanium is present in 4th period. Germanium is present in 4th period. And here is the number 2. Number 2 means germanium is placed in the second column of the P block element, or you may call the second group of the P block element. Similarly, and the possession of the p orbital, as these all colors show a p orbital. Here you may see there are some other information also, that it has 3d electron, that these 10 elements are filled, or these 10 electron are filled. So here you may see here also that the 2s block orbital electron are also here, the 4s2 and the 3d 10 electron. So all the electronic configuration here now will give you a message. So basically an ending orbital give you the position of the element in the periodic table, or simply you may call the address of the element in the periodic table. So this is, we have some of the groups present in the periodic table, and we have discussed some of the group in the later our lecture. For example, as we have the alkali metal, alkaline earth metal second group, this role as a transition element, including with outer and inner transition element are allocated. There are p block elements, some of the chalcogen, some of the halogen, some of the noble, and some of the common element which are present here. So this is all about some of the basic features of the electron configuration, some of the basic information of the periodic table, and some of the electronic configuration about the locating the element in the periodic table.